So this is a overview of the R.I.D.E product that goes into the larger shop score platform. I'll show some architecture diagrams, code, logs, and do a sample run of some of the systems. In a separate video, I'll go over some of the business perspectives and just the overall product overview. This is strictly technical overview, since the code can't be open sourced for reasons explained elsewhere. At least this will provide some visibility onto the technology that was built. So the R.I.D.E product evolved quite a bit from Q1 to Q2, Q3, and Q4 in 2019, but it was in production as early as Q1 of 2019. And I will show quite a bit of code. Some of that will be the code that's in production, and I'll provide some details on various versions and improvements of that code that's not fully implemented, that I'm going to probably skip because some of these improvements will just require a lot of switching of screens and partial views and so on, and I'd rather at least show the full flow. And I will show some of the logs and the runs of some initial versions of that flow as far back as Q1 of 2019. So I used Lucidchart for a lot of the architecture diagrams. There's quite a few here. I'm just going to focus on the one that's relevant for today. The flow that is in production, as you can see, I've boxed it because that is implemented. The implementation I'm going to show is currently on Amazon AWS. But the backbone model is a hybrid model. So there are quite a few additional elements that pertain to our hybrid implementation. Today, I'm going to just demonstrate what's in production on AWS, is what you see right here in the front. So the input files, which are stored in an S3 instance, are in JSON and image format. We'll be just ingesting the JSON format here. And there are quite a few additional functionalities, especially for the image files, that I'm not going to go into today. So you see some of the thicker lines indicating the main flow, and that's what I'm going to discuss today. The JSON data is data that is scraped from the websites, and it looks like this. And this is an older version of the format. The format has evolved a little bit, but at least I want to give a sense of what the JSON files that we're ingesting look like. They have a variety of elements: the retailer, the product ID, the category hierarchy, which is a key entry in the JSON, the URL title, the description text, which can be used for extracting a lot of information using NLP, the brand color, an array of sizes, price, the images associated with the SKU, and a lot of related products. In this case, is a complete look. There are also bought with products that are brought together with the original product, similar products, and various products based on customer actions and recommendations. This is an abbreviated version. In the current data, all of these are fully pulled from the websites and typically range in hundreds to thousands to tens of thousands of lists. An array of tens of thousands of items, but at least in this example from probably even late 2018, This was an example of one of the JSON files. The um, the the product ID or the SKU ID, all of this gets mined and converted significantly, but in some cases, a JSON file will represent what we call the parent SKU, which means it represents really a group of products that are related either by the same SKU and they represent different sizes, sometimes different colors, sometimes different variations. And it really depends on the website, especially Amazon has that parent child relationship between the parent SKU in terms of the parent product ID and the child product ID, as well as we saw this with Bloomingdale's and Nordstrom and other websites. So a JSON is not necessarily representative of what we think of an item. It could represent a collection of items, sometimes depending on the depth and variation. With Amazon especially, could be dozens and dozens of items. So the current flow that I'm going to go over ingests these images from a coupling with S3 into an EC2 instance, and their modules, which you can think of series of scripts. The main one that starts is a parallelized parsing module that filters, cleans the JSONs, makes sure that we only ingest JSONs with proper entries and that satisfies certain requirements. We would like the JSONs to have some of the main elements like brand, retailer, and category hierarchy and SKU ID. This is just an older version of the pipeline, which was leveraging data that was inherited from prior to the build of the pipeline, which was called cold data, and it would be ingested in batches, and the hot data, which would be currently scraped data. So the next function, which is the parsing, is effectively the translation from a JSON file format of each individual item, standardizing all the entries and entering them into a relational or a table format. The next one is category detection. That is a fairly sophisticated module and has undergone significant changes over the course of 2019. Currently, it's multi-threaded, multi-core, parallelized, and it's fully implemented in Python. I'll show the R version, which was kind of in the initial version, but we have the more sophisticated version. It is a combination of rule-based filters that detect the category according to our taxonomy model. You can see the taxonomy model informs this entire module and specifically the category detection. It does not implement an NLP algorithm, which comes later, which has some probabilistic and finer functionality. This is more rule-based, and also it applies some filters and transformations. There is a final transformations module, which applies certain filters, such as, for example, if a brand only has a couple of items, that's a really just kind of a peripheral brand that's probably not relevant, or it's some kind of anomaly, so we want to filter it out. Also, variations in the names of brands because they're misspelled or spelled differently in different retailers. Also, the color scheme is completely different from retailer to retailer, so we have a standardization of that, and also the retailer name even. So we make sure that all of that is taken care of. That all of that is used for generating training data, also feeds some pre-tagged image data that is more on the cold side, I'd say. And that all feeds into the subsequent on-premises architecture as part of the hybrid module. But this is more of an output. After we do all the transformations, of course, there is a loop here which has a new category detection. I'm not going to discuss this because some of that is not fully developed and productionalized, but basically this feedback loop that you see here allows us to look for categories that basically are new and maybe weren't represented in the previous taxonomy. And there is reinforcement learning element to this because there's self-learning, basically self-discovering new categories, classes, styles, and so on of the data, and that informs um, subsequent runs of the data. So then we get to a very critical module, which is the parsing of the SKU pairs. I showed earlier that each SKU comes with a list of similar SKUs, pair with, bought with, recommended, and so on and so forth. And that needs to be parsed in order to be fed into the data fabric model. So, or concurrence module, that's a graph-based model. So for that, we need to extract this as a massive list of pairs. So that is fairly sophisticated. It needs to be done in parallel. It needs to be validated. It needs to be also symmetric, which has caused significant challenges in the past, but we were able to implement additional functions. I will show the functions that take care of that. So as a result of that, you not only have a relational table with a list of all these elements, but you also have an edge list of uh, tens of millions, hundreds of millions of connections between these items that can be further aggregated at the category, brand, retailer level. So this co-occurrence module extracts these relationships and some of these aggregated relationships um, because the dimensions are vastly different from the previous relational table. So that requires a separate calculation, and it's an example of the first pipeline that we push all the way to the Elastic Index and to Kibana. So the Elastic database is launched on using enterprise implementation from Elastic, and that is runs on a GCP, in fact, backend. But because the implementation is really from Elastic, it's irrelevant whether it was AWS or GCP. We chose GCP just to have it on a different cloud. But this is one of the, there are 6 overall pipelines, but right now the 4 ones are the ones that are fully automated. So after we do the co-occurrence, which branches out, we get to the global module. And the global model really looks at the entire data fabric. It in fact generates the data fabric industry-wide. And then implements some network metrics, which I will show, and also generates some global brand metrics, which are the most dominant brands globally, which are the most dominant items, categories, styles, and so on. That global module basically gives each item, each category, each brand sort of a metrics that are about this brand as it sits within the entire ecosystem, within the entire industry. So that could be useful because we want to look at especially e-commerce, fashion, retail as an ecosystem. And then the local module is really carrying out the same type of calculations, but looking at those at each retailer locally. So that's necessary because retailers would like to see the the most dominant brands or the strongest, weakest, influential, critical, and so on, and other brands according to our data fabric. Where basically we create a local data fabric for each retailer. It's not really for every single retailer. There's a cutoff. We probably get the first few thousand retailers, but the most relevant ones are probably even the first dozen or so. eBay, Amazon, Walmart, Macy's, Target, Nordstrom, and so on. Really, that can also be implemented if the client is a particular retailer for 21 or Eddie Bauer or Steve Madden or some specific retailer that needs that implemented. If for some reason the threshold did not include them, then we can just custom trigger this and run this implementation. Then we get to this X factor module, and that's a very interesting one. It's actually one of the more challenging algorithms because it looks at one retailer and the brands within that retailer, and it looks at all external brands, brands that are not well represented within the retailer. And so if this retailer wants to introduce a new brand or a new item or a new category into their um, catalog, we rank all of these candidates, right? And according to the retailer's already existing categories, brands, and items, and looking at how they interact with that new candidate category or item or brand globally. So we don't want to introduce direct substitutes because then they will just cannibalize the customers. We actually want to introduce external brands and items that will boost the existing items and brands, will make customers purchase them, increase the customer baskets, make customers visit the store more frequently, visit the website more frequently, and buy larger baskets and so on and so forth. So that's what we're looking for, and we are able to not only find those out, but we're able to in fact rank them. And I will show how that works, and I will go over the code, and I will also show the a log output that actually kind of shows some of these examples. I'll go over the elastic, or I may even defer that to another video, which is more on the output. And I really wanted to make sure that we focus on these modules here. So currently, let me see, is there anything else that I wanted to show? I have the log, I have that. Yeah, so that's good. Currently, we have a very basic sized EC2 implementation running just for the purposes of this demo. I think it's 128 gigabytes, and so let me just log in. Nothing unusual here, just using the standard terminal. So I think we've got 16 cores, 128 gigabytes. I wanted to show a screenshot of the same instance, the same pipeline, but with a 48 core. I think it was it 512 or was it 380, something like that. So this was an implementation of a multi-core multi-threaded calculation. I believe it was the parsing algorithm, but I can't recall. Regardless, we would inflate that EC2 instance to be able to carry out these massive calculations on demand, but then shut it down or scale it down if we didn't need those. So it's a Linux instance. It's got R, Python, that's it. So anyway, this is what it typically worked. look like. And right now I will just show the one that's with just these 16 cores. So let's take a look. So the core code, which is linked to the repo, is in the R.I.D.E prod repository. You see there are quite a few R scripts here, and I will explain some of them. I will just show just the pipeline that effectively runs the shell scripts that effectively trigger this pipeline and execute the majority of these. When I say the majority, some of these are manual with the lean arrows, so some of these are not going to get triggered. So I will show that, and then we'll take a look at the code. So the shell script, it's a very simple, you can just use cron or whatever to schedule it. The shell script, I think we can use, let's look at the start pipeline. I think that's a reasonable one. So what you see here is, first of all, making sure there are no existing R scripts, because sometimes if you have multiple triggers of the same pipeline, it just overlaps and creates a lot of issues with the intermediate tables that are written. Then right here we've got the elastic credentials, but also we've got the pairing right here, the very last line, of the JSON files. As I mentioned, I'm not going to go over the image files. We get the pairing of the JSON files, so that gets pulled into the EC2 instance. And actually, let me show that real quick. This is an instance that is attached to it. I think that's what it was. Right. Yeah, so you're going to see here a lot of folders. So for example, the blue ones are folders of some of the main retailers that contain the JSON data. You see a lot of intermediate data frames that get some of them also are the code data that I mentioned is ingested as batches. That's no longer in the production, but in Q1 of 2019 it was. You see the color dictionary, which gets expanded, overwritten, and implemented. You see some output tables, especially the ones that are in CSV format, are the ones that get transferred into a new kind of JSON that is compatible and prepped for ingestion into Elasticsearch. I will show that. And you've got some of the output of the category and color standardization, an intermediate parameters table, which I'll explain how it works, and this SKU master table, which is, you will see examples of that, which is that relational table that I mentioned in the beginning after we parse the JSONs on the input. And you've got the universal SKU catalog model. That is something I wanted to quickly, briefly show, because it's a significant component here. Basically, it allows the standardization of SKUs in a global way that come from various retailers, but really are the same thing, like a Hanes t-shirt that is sold at Walmart, Macy's, and Target. It's short sleeves, crew neck, white color, 100% cotton, everything is the same, but it might be labeled differently. It might have a different local retailer ID based on the retailer, but we are able to map it to a universal representation so that we can recognize it across retailers. So that table, and as you can see, this is one-to-many relationships here. It has to be two-way relationships, so you can actually recover all the list of all original source SKUs here, and so on and so forth. So the table that I showed right here is relevant to that. So once the syncing happens, basically we trigger a lot of scripts. As I mentioned, in Q1 of 2019, a lot of those are written in R. Now, about half of that code is already translated in Python, which is my preferred production language. However, a lot of the analysis was done in R, and especially it has a lot of network analysis. So that's the reason for this initial code existing in R, and we went very rapidly to productionalize it, and so that's what I'll show. Now, the function push data to index, this function effectively sends the data using the Elasticsearch credentials to the, as I mentioned, the four Elastic indices using the Elasticsearch loader command here with various attributes. And these are the four indexes that are created using this command. Now, and then obviously that's available in Kibana, and that has been used to generate reports, analysis, dashboards for clients and potential investors, partners who want to just play around with the data, see what the data looks like, see the depth and the dimensions of the data. So triggering this, basically using cron, you can schedule it, effectively gives you the full automation. Now, this is production, but I say probably it's a very lean version of production. And that's because we need quite a bit more to be able to have stability, scalability, and also monitor the overall health of the system. So one thing that I wanted to show here that I thought was very useful, because the business part of the team who couldn't bother logging in and going through all of these technical checks and looking at log files and so on and so forth. I'll show you what a log file looks like. I wanted to make it easy for them to just see some output each time we ran the system, especially initially when it was triggered manually before it became scheduled. So I created an output, and I wanted to show that, an output to a Slack channel called R.I.D.E Alerts. And back in March, this was just a very basic thing. It just says the run started at this time, and here are the number of SKUs. Obviously, I was testing with with a sample SKUs, and here are the number of brands, and here are the number of links. And you see, initially we started maybe with like 1 million SKUs and however many links. And each time there was a run, there was an alert. Now, these alerts became a little bit more sophisticated, but I wanted to show you already as far as March, this was the system that we used, and it ran end to end. Obviously, I would find improvements, I would find some data errors that need correcting, and so on and so forth. And this was a way for all of us to kind of keep an eye on our system and make sure that it worked. So let's scroll down through maybe end of March. We're starting to look at 2.8 million SKUs, including colors, but not sizes and size variations. So that's quote unquote pair SKUs and 57,000 brands. And when I say filtered, I mean, as I mentioned, you clean up the names, the variations of the brands, and you also filter brands that are peripheral with very few SKUs. All of that has persisted since, and you can see the growth of the figures. Later on, we are able to see, in fact, the universal SKU catalog size, these abstract universal SKUs, and also break down by category of the different SKUs, and some categories were underrepresented and so on and so forth, all the way to more recent times where this was starting to yield some more significant, more sophisticated results with larger number of SKUs and larger number of brands. So this is July. Let's look at October. Now you're looking at 40 million parent SKUs, which is maybe in the 400 million total SKUs if you look at all the variations, and so on and so forth. And you're looking at hundreds of 800,000 brands, or maybe 300 after after filters and breakdown by a much larger number of categories here. In the end, we ended up with about 70 or so categories and so on. So I wanted to show this because this was how the technical part of the team kept the entire team appraised of what was going on with our production system. That level of transparency was really important and is always important because it gives the business team information and the ability to really see what's going on without having to log in and do all the technical stuff. Okay, so I wanted to show the code, and I'm going to show the code straight from the actual instance here, just because I think it's important for everyone to see that. And I might refer to some notes that I have elsewhere, and I might refer to the documentation here as well. But we'll start with the data ingestion and parsing module. So let me just keep this this off to the side here so I can refer to that. Okay. So if you take a look, so ingest and parse JSON data, here it is. Let's take a look at what's in this code. Oh, first I have to go back. I apologize. I have to go back to the pipeline, and I have to explain this R.I.D.E global parameters function. Okay, so I want to explain that because that triggers and loads into memory a massive module of functions in the background that feeds into all of these other modules. So actually, I'm going to take this and maybe give it, keep it here. Okay, so okay. All right, so in this case, We ignore some of these. We're going to read this parameters table. And unfortunately, that table I cannot quite show here, but the table contains some values of where the uh, um, default the home directory is, and calls up the function that contains basically all the R script that contains all the other functions, all the significant functions that we need. So it specifies the source path. So the parameters table basically gives you the source path, it gives you the working directory, and gives you the basically the location of all the JSONs. So then before I get into the parsing of the JSONs, or maybe as I'm doing that, I would like to pull up that that massive function so we can look that up. It's called R.I.D.E global functions, and it's, as you can see, much significantly larger than any other file. So as we look through this, what I'll do is I'll refer to this function and to places and various parts of the function. The function is about 6,000 or 7,000 lines of code. It really covers pretty much some of the most significant uh, functionality that goes into the code, especially when we talk about parsing, when we talk about the network analysis and the analytics that basically extracts the intelligence from the data. So if you look at this, we read the JSON files and we print them. I should, in parallel, actually pull up the the log file so you can see what the output looks like as well. Yeah. So. Right. So as you execute this script, you know, it says, okay, print, start reading JSONs, done reading JSONs. So here you have start reading JSONs and done reading JSONs. Why do we do that? In case the data, which is very noisy, retail data is super noisy, in case that gives some kind of error, or there is some kind of infrastructure error, we would like to be able to locate that. So this one is, I forget, this was a trial run, 4 million JSONs. Ignore the numbers, but at least we are able to see what's going on here. And we save the JSONs, and basically that gets completed. But behind the scenes, there is cleanup JSONs, dropped empty JSON files. So the clean JSONs, for example, is a function that it may be not as practical to actually do this because these are not quite in, they're kind of in order, but they're not quite in order. So let's just stick with this and see if maybe I need to pull it up using some other interface. But clean JSONs, it's a multi-threaded, multi-core implementation. It looks at the length of the JSON file, how many entries are in there. An array could be an entry, an element could be an entry, and basically it uses a certain threshold that we ingest to remove these. So initially, it's the sizes that are no or zero that get thrown out, And subsequently, if you look at get JSON lengths file and clean up the JSONs, basically the JSON length, I think, is 4 or something like that. We need at least the 4 entries. So these two functions basically take care of that. So that all of that is a fairly trivial thing, but it scales so it can run with tens or hundreds of millions of JSONs in parallel, using all the cores, multi-threaded. So I think there is some sort of limit to this where we get to billions of JSONs or maybe tens of billions of JSONs, and even having 100 cores or 200 cores, at some point the system will start kind of choking. We never reached that limit. I think it's probably in the 10 or 100 billion range. So that is, there's plenty of space ceiling to go for. Okay, so that's that. And by calling this, basically all of these functions become resonant in memory. So the next thing is ingest and parse. So we just did that, sorry. Adding cold and hot data. That's a little outdated. Let's take a look at that. But it's really, as I mentioned, there's some batch data. So it's not JSON data, it's batch data. So as you can see, it ingests specific tables which are pre-calculated already. This is data that we inherited, and makes sure that they're all standardized and they all fit in one large batch table, which we used initially because we were growing our scraping capabilities, and this data was already scraped in the past historically. Anyway, this parse SKU master data is one of the most important files here. It's a fairly significant file, and it's got quite a bit of work. Although it seems like it's nothing, it's actually quite significant. So again, we ingest all the JSONs, and we do a little bit of transformations of the IDs because they're all quite messy. But there is these transformations are fairly trivial. What I'm looking for is the transformation that extracts and it parses the SKUs. Oh, so, okay, yeah, so this is the ingestion of the hot cold data batch. This gets the cat strings, but actually I need the parsing of the SKUs, which should have already happened, and that's a significant one. I wonder if I just don't. Just take a look. So all of these are really subsequent once we actually have created the relational. So I'm looking for the implementation of this function, and I'll go back in a second and find in which script that is. It should have already happened. So this is significant because what you're seeing here is a function that parses a single SKU, And what you're seeing here, oh yeah, that already happened in the first file, and I just overlooked it for a second because they're wrapped into each other. So the SKU catalog function uses the parse SKU function, but it runs it in the multi-threaded, multi-core way, and it, uh, it parses each JSON file into a relational table, but it does that in a multi-threaded, multi-core way very, very, very rapidly. And it also does a little bit of transformation and filtering in case there's, because the data has got a lot of noise. And I apologize, this actually is here, just parse JSON data. I think I overlooked it. Let me just go back. Yeah, so build the university catalog. So you have this. So the files are really all the JSONs listed as a list. And you applying the SKU catalog function. That function is the function that takes the parsing function into a multi-core, multi-threaded implementation and basically gets you from JSONs to a relational table, which becomes the source of, and as I call it, the SKU master data. It becomes the source of the master data. So you can see here that the log file shows that ran. You have 30, what is it, 3.8 million, because there was some filtering. You started with 4 million JSONs, but only 3.8 were really non-empty and reasonable. And you have 13 attributes, which are, you can see this: category, title, brand, color, price, blah, 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 blah. So all of that was in the first script. The second script, as I mentioned, adds the hot and cold data. And now in the third script, which I had pulled up, which is parsing the SKU master data, that script actually does some cleanup. So it cleans the titles. So let's take a look at the cleaning of the titles, because that one actually is I think that's where we're going to get in trouble trying to like find all of these. I have these kind of taxonomy functions. So instead of doing that, what I'll do is I'll just pull that up and actually we'll be able to search and see what the function looks like. So the function, for example, that says trim title, right? So something like this, it's a function that makes sure there are no line breaks, there are no multiple space entries into the title, and so on and so forth. So that's one example. What was another example in this log file? So we trim the title, we clean up the SKU titles, we remove the extra spacing. So something like remove spacing, rem sp. Of course, this is a little amateurish initially when you're doing all of the development, and some of the names are a little bit so this removes multiple spaces, remove the extra spacing, select the first 100 characters. So that's actually kind of important. That one, I introduced it because sometimes the parsing of the JSON, when you have the title and you have the description, and the description gets parsed into the title and gives you like lines and lines and paragraphs, and that just kind of didn't work. So there's something to try to control that. And there are a bunch of other things, like select the first 100 words or the first 5 words from the title. So I actually have this get words to, and that was actually a non-trivial thing because you have to figure out what is a word, right, in a title. And then you have to make sure that there's a single space between the words, and then count the words, but don't count like one letter words, because, right, it's kind of, so anyway, some of these functions take care of that. And um, I'm going to ignore, there's some cat strings and something like that, category strings, which was an intermediate table. And you can see at the end of each one of these scripts, we're saving these intermediate tables. And that was the long folder with all the intermediate tables that I showed. And the reason why we do that is because it allows, if there are errors, we don't have to go back to the original run. We can kind of pick up from the middle and see, which table where we left off. We are able to kind of modularize this. And I'm a big fan of this because having one endless script that produces a single error and you have to start over, and the runtime sometimes is days or even weeks, it's just really impractical. So great. So then we get to category detection. I'm going to be a little bit brief because this is already kind of getting a little monotonous, but category detection is really a script which applies, I think in the R version, basically it applied a lot of hard rules that are based on the taxonomy model. The good news about that is that the taxonomy then, when we develop the reinforcement learning, can automatically update those hard rules without human intervention based on new dominant categories or words or descriptions. So I'm just going to quickly get through that. I'm not going to go too much in detail, but get cats 0 is the function that is being used. Oh, sorry. Get cats 0. And you see that this function uses a bunch of intermediate functions that are each one is kind of assigned a different category. And you can see why is there a 0 and then there's a 1 and there's a 2, because depending on, it was done initially in 3 waves, all of that much improved using the Python code, but I'm not going to go over it right now. 3 waves based on the types of associations and rules we were using in each wave. So 0 was a little bit less stringent, and then 1 and 2 became very, very significant. So you can see, for example, a category we would like to eliminate is kids and juniors. And for that, keywords like kid, junior, boy, girl, or young, or combinations of those would be searched in the description, in the title, and in the category string path of the JSON. And if there was a hit, an exact hit, we would classify this as kids and juniors and basically exclude this from our taxonomy because we weren't delivering that. Athletic shoes, you see all the, basically all the hard rules. So all of that in extensive detail basically gives you the category detection. And at that point, you basically have a relational table that has the retailer, SKU ID, gender, class, category, subcategory, and so on. And it's got title, brand, color, price, description, and the old category. And when I say old category, this is the category that came with the from the retailer's own taxonomy. And the new category is the category according to our proprietary taxonomy. So one of the outputs from this script is a breakdown of the category counts by category, and then you see the further refinement. One thing that this taught us was to look at the category other. So other is a category which basically you've done all the SKUs that have not been classified. As you go through these different levels of classification, other should diminish. So other was 6.4 million, and now it's 6 million, and I forget. Then it gets lower and lower and lower with subsequent iterations. But there is a finite limit. At some point, you have classified everything you can classify, and this other becomes just kind of the noise. Sometimes in there is some noise because the retailer linked, I don't know, non-apparel items with apparel items. Or, but it could be that there is a new category like umbrellas, which is a type of accessory that will emerge that we might not have in the current taxonomy. So we would further data mine that other initially manually, and then you automate that, and you just do frequency analysis of the types of keywords and new categories in there, and that can further be automated, as I mentioned, this reinforcement learning framework that can insert new categories and grow your taxonomy that way. So at that point, we have gotten as far as the final transformations. So let's take a look at these final transformations. Some of these, you can see there's quite a bit here, but a lot of these are kind of trivial. We would fix the brands, and fixing the brands, let's take a look at what that does. Loading the data, export the train data, short description, blah, 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 brand transformation. Drop brands, drop short brands, format brands. So let me give you an example of what that means. Drop brands is basically a function where specific explicit brands are going to be dropped because they exist. They are generated, like system generated or something like that. Drop short brands is one that, as I mentioned, brands that I think it might be that I might have absorbed this under format brands, and I apologize. This log, the code that I'm showing here is a little bit outdated from the code that's in production, but I just have that I just have that handy. So 1 second, let me see. I'm not gonna. So so you can see something here, which is kind of a very extensive list of manually generated brand transformations. It's for each letter, you have a different brand transformation, and they're all wrapped in the function trim brand and the function format brands. So I thought that format brands, I would be able to format brands, and I thought it should pop up, but for some reason I couldn't look it up. So format brands makes them all upper, removes some formatting based on like the source of the environment that they came, some extensive spacing that would be there, the trim brand is there, and then remove the spacing, and then you've got this by letter. And that's because it's absolutely crazy. Things like Tommy Hilfiger or Victoria's Secret or Michael Kors or Nike, you just have all kinds of variations of that brand. Now, this is very difficult to automate because you really need expertise here to know which variations should be fixed and which ones are, maybe there was a brand campaign that was run, and that's why it's got an extra name there. So Calvin Klein collection, maybe there was a campaign plus sizes for Calvin Klein performance. So should we leave that as a separate brand? Is that a standalone business? So quite a bit of work went into that brand standardization. Uh, then formatting brands and so on and so forth. Then we have some, here's an example of what the output looks like actually. You've got the retailer, you have the SKU ID, which contains the specific number to the retailer, and then you have the retailer up there. You have the class, the category, brand color, description, which is fairly shrunk. That description is kind of a subset of the full description, the full paragraph that you guys saw, and there's some other stuff. So the description, the colors, that's a little tricky. It depends on the data model. For some purposes, I left the description in the full length. For data mining, you see that we are ingesting it. But when we get to like pushing this to like Kibana, Kibana and Elastic, they're not going to display a description like on a graph that's like a paragraph long. So something like that isn't going to work there. So for that reason, for purposes of like dashboarding, the description had to be formatted. So similarly, we had to format the titles of retailers, and the colors had to be also standardized, and also just some more brand cleanup and some filtering of the data, as well as this was the push to Slack, and that, and also the push to the continuous push to the log file. So I think this is pretty good overview of where we're at, and at this point we have reviewed. Let's see how far we've gotten. We've reviewed the ingestion and the final transformations. We've basically reviewed this part right here. We're going to now get to the SKU pairs, co-currents, global, local, and external models. So let's see. Parsing of the SKU pairs is actually fairly significant because it allows us to really build the network model from basically a list of pairs. So let's take a look at what that is. We're getting the bot with relationships and some other relationships. So let's see some of the functions that are in here. So again, this has to be done in parallel. Otherwise, you just there's no hope. So you can see that I apply that, and one of the first key functions here is get bot with. So get bot with actually looks back at the JSON, looks at the particular type of relationship between the original SKU and the array of SKUs, and extracts them and parses them. And that had to go through multiple variations because it's very finicky and it needs to be stabilized. And then there is another function that is kind of critical, which is called split it. That function, for some reason, again, I'm not able to search it. I don't know why. Maybe I need to, let me see. Um, yeah, there you go. So for some reason, when I copy and paste, it just doesn't recognize the formatting. So that function had to undergo significant changes. So the way I did it was I actually would list the pair of the first SKU and the second SKU kind of as a single string so I can control it better, and then subsequently split it into a list of ordered pairs of SKUs. So that split it is the function that does that, and depending on what I needed to do, I had a second version there. And let's see, I think that plus some trivial formats really took care of the majority of the work. here. And so now I have some initial stats, but basically this is what we get. The output looks like just an ordered pairs of SKUs, and that can be hundreds of millions, into the hundreds of millions. So now we would be ready to basically, oh yeah, I need to show the co-occurrence model. It gets very tricky. So I'm actually going to try to keep this fairly quick here. The co-occurrence model, we start with the master data, right? And it's got some I've already done the calculation. So let's just take a look at here, because this is, so I start with the relational table, I ingest that, and then I create something called the co-occurrence brand data. That co-occurrence brand data has, and I was really hoping that I have that as an intermediate output. I don't know why I don't have that. But that co-occurrence brand data has a, oh yeah, there you go. It's kind of here, but it's kind of hard to see. It's the brand and the co-occurrence brand. So depending on which one you want to query, it's kind of symmetric, but you have to be careful. So for example, Nike co-occurrence with Nike at the retailer eBay, and these are the categories, and Adidas co-occurrence with Adidas at the retailer eBay, and these are the categories. So that's what we get. And then we get into a very tricky piece, which is the actual aggregated co-occurrence of brands, which means all the different combinations of pairs of SKUs from one brand and another brand. And that, I would say, is a non-trivial thing to do. And I wanted to show the function for that. So this is the function. As I mentioned, it's a non-trivial function that does the aggregation at multiple levels, at the category level, at the brand level. So you can see that we actually have some of the counts and they get converted to percentages. I'm not going to go into too much detail, but there were probably another dozen of metrics that I just cut from that because it was getting very, 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 very technical. And typically for business end users and for clients, they would probably just want the ranked table of the external brands. But that allows us to just get the data fabric at the category or brand or retailer level. So I'm going to go to the global model, trying to just wrap this up a little bit faster here because we're going to get to some very interesting work here. But it's getting a little bit technical. So again, I start with the relations, data catalog. There are some aggregations, nothing really critical until we get to this. So the intermediate calculations here, which I should have entitled somewhere, brand attribution, percent representation per brand, brand master data, brand attribution, SKU counts per retailer per brand. All of these are, SKU percentages per retailer per brand. Like this is like how many SKUs are in each retailer, in each brand. Like that's really nothing earth-shattering. But now we get to network-based attribution, and that gets interesting. So the first thing is the brand co-occurrence. So let me see again. Brand co. So that actually sets us up with the and the brand size. This sets us up with some basic aggregations and get edge size. That's also an aggregation. And I'm gonna get to get network metrics. So that was something. Oh yeah, that is right here actually. So that's something that I actually wanted to review in a little bit more detail, because to get this to perform at scale and multi-thread, multi-core required some work. So this actually generates a graph object, and there is a limit to this. I think we can get probably to the hundreds of millions, and then probably, I mean, there's a theoretical limit maybe in the 10 billion, but actually when you get to a billion, it may need to be done in a graph database. So you may need an actual architecture that supports this model. We never got to that, so we're fine here in the 100 million to billion. Once you get to 10, 100 billion, you may need to implement that, or Julia using Spark, GraphX, or just any kind of data stacks has that. There are a bunch of other graph architectures. I expected I expect that with half a dozen clients, that's not going to be necessary. When you get to a dozen clients or 12 months beyond this point, you will get into the 10 billion or 100 billion, and you may need to actually re-engineer this. So we extract several basic metrics like the degree and the weighted degree, the centrality metrics like eigenvector, neighborhood centrality, closeness and betweenness centrality. I actually removed the closeness because it was not really giving us anything that we couldn't derive from the rest. Transitivity and some others. So all of these are theoretically described in a very early version. They're available. They're fairly standard metrics. Long in the early stages of some of my postings, I posted some theoretical overviews of these where we can, we can kind of just see what's going on. But really what I want to show is right here, kind of a cleaned up summary of these, because that will be helpful just to see what's going on. So when I say the network setup, I actually describe, these are very, 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 very early versions of the code. And I define some of these. In the global model that you're seeing right now, we've got, I'm talking about like what it does and all these things and basic filters and all of that. Here, the basic SKU counts, industry-wide aggregations and all that. And then we get to this. So the network degree, the number of brand vertices or SKU vertices or category vertices connected to a given brand vertex. So this was done at the brand level. I aggregated up, but it can be done at any level. Each connection is of weight 1, indicating brand-to-brand co-occurrence. Now you have a weighted one. Now that takes into account all the numbers of SKU pairs. The eigenvector centrality is a measure of the influence of a node in a network. It assigns relative scores to all nodes in the network based on the concept that connections to high-scoring nodes contribute more to the score of the given node, and so on. This is basically a version of Google PageRank, right? The websites that are linked to very famous websites or very high traffic websites are actually have a higher rank, even if they themselves don't get much traffic. The neighborhood size gives you a little bit of a local measure of what's going on. So when you want to interpret that in the context of retail, basically you're looking at the footprint of a small part of the customer base. So it's not just a single type of basket, but it's maybe a cluster of baskets, and that can give rise to what we call an occasion or a type of shopper. So it might be everyday baskets like milk, bread, and so on for the grocery, or you might have sports baskets. And it's not just one sports basket, it's like a cluster of baskets all revolving around sneakers, sportswear, performance wear, athleisure, whatever. So we use all of these metrics to actually, in a very standard way. I didn't invent any of these. These are well known. I've worked with some of the inventors of these, but I am not the author of these. Any one of these metrics are well known for the last 20 years or so in the industry. So these are just kind of, if you will, the standard tools for extracting the intelligence at a very basic level. Then we have another layer that of proprietary metrics that actually use these and some of the other ones to give us the real interpretive metrics like strength and so on and so forth. And at that point, that is done at the global level. So we've got the brand strength. Where is that? Yeah, there you go. Generate the SKU metrics, the graph object, the basic metrics, the weighted degree, and like all of that, closeness and all the centralities. And then from there, I get the proprietary metrics, which give us the brand strength, influence, and hub, which means criticality. There were another at least 24 metrics that I basically depreciated for this initial version because just the depth and the breadth is unnecessary when we go very fast to production. And in some of this Confluence work, which is on the internal private space here, the goal was to also kind of create kind of a manual for new developers or team members, technical team members that they can refer to, so they're not just staring at the raw code like that and wondering what the heck is going on. So the local model, as I mentioned, it's kind of a similar version, but it actually iterates over a over each of some of the top retailers. I forget. What do we have here? Walmart. I showed Walmart here, but that's the local model. Fairly similar, I'd say. So there isn't anything really earth-shattering. The network metrics would run there, and then there's the yeah, and and then we have this model, and this was particularly challenging because you need to look at this was particularly challenging because although it looks short, it's actually fairly complicated. You need to get these metrics, but you need to kind of group the brands into internal and external brands and look at pairs of brands or items or categories that are internal, external, and then find their interaction. Basically, are shoppers putting them in the same baskets elsewhere, right? So you're looking at the given retailer, take Macy's, and you want to look at a brand that Macy's doesn't have, although Macy's is not a good example, it's very large, but take a Forever 21 or some smaller retailer, and they need a new brand or a new type of item or category that they want to bring into their catalog. Now you're looking at all of those externally, and then you're looking at what they already have, and you're looking at if they have that elsewhere, and is that new brand or category they want elsewhere as well, like at Amazon, which has everything. And now, what are the baskets looking like? Are customers really buying these two together? Compare then the baskets from the current retailer to the other retailer, similar baskets. And now you're starting to find, well, is there growth opportunity here? Are the ones baskets of the current retailer found elsewhere with the additional brand larger? Do we have a wider customer base, and so on and so forth? So I wanted to maybe take one of the functions or something like that and see, get network metrics. Yeah, there's an I metrics and X metrics. So uh, there's the I metrics is a ranking of the internal brands. The X metrics is a way to rank the external brands relative to the internal brands. And that's what's happening here. It's a pretty involved calculation um, that pretty much takes the rest of the, because it lists each retailer individually, and like Banana Republic. So you're starting to see like the weighted degree, the centrality metrics, but you're actually using them to actually derive these external relative metrics. So that was kind of that's kind of the interesting variation here, because they're all relative. They're not actually the same as the local metrics. So if you look at, so what I'm trying to say is that if you look at, I might have skimmed through that. If you look at a given retailer, if you look at a given retailer and you look at brands that are underrepresented or unavailable, you're going to start to find the various rankings of those brands relative to their internal brands. I think you've got the internal brands here, and then you're going to have the external brands relative to these internal brands ranked as well. So that is part of what gets pushed to the Elasticsearch, and that generates the recommendations. I think I'm going to stop here because this video is starting to be fairly extensive. Here's the original version. This is a little bit outdated of all the functions, and pretty much that's the just kind of a high look at some of the work here um, on the production pipeline that happened back in Q1 of 2019, with further iterations in Q2 and Q3. And of course, this is all internal. It's not going to be open sourced. It wasn't going to be open sourced at the time. Now there are other restrictions, but the code is there, the work's there, and it allowed us to have this initial product and start generating dashboards, insights. Maybe the API wasn't ready then, but we were able to at least have the output and start generating some of the reports that we have shown, and that allowed us to envision an end-to-end product, envision use cases, and even start talking to potential clients, potential investors, and mentors, just so that we can get into the process of iterating over. So getting zero to actually launch is very, very important. So even if it's our code, even if it's not as pretty, what it allows you to do is have a framework that you can that you get so quickly to implementation, that but still you have scalability, you have the ability to iterate over and improve, and you have the flexibility to make changes and improvements, and maybe even pivot a little if some of the calculations or attributes are unnecessary. Like initially I had about 100 attributes, they're down to about a dozen now, based on feedback, right? So that was the really important thing, that we've been iterating over this since Q1. And I think that deserved an overview and at least this kind of detail analysis and recognition that it exists, and it's a real thing.